NEC Table 450.3 addresses the overcurrent protection requirements for transformers. It stipulates that the primary overcurrent protection device, or OCPD, should be sized at 125% of the transformer's full load current, or FLA, if only primary protection is provided. However, if both primary and secondary protection are in place, the primary OCPD can be sized up to 250% of the transformer's FLA. Now, a pertinent question arises: what if the load on the secondary side is minimal and consistent? In such scenarios, it becomes feasible to set the primary OCPD closer to the transformer's FLA. The motivation behind this adjustment is often to reduce expenses associated with the OCPD. It's important to consider the inrush current that a transformer experiences when it is initially energized. This inrush current is influenced by various factors, including the transformer's size, design, and the specific load conditions. Generally speaking, smaller transformers, those under 75 kV, tend to exhibit less severe inrush currents compared to their larger counterparts. When dealing with smaller transformers that supply a consistent and low secondary load, it might be viable to set the primary OCPD to around 95% of the transformer's FLA. However, it is crucial to recognize that this is not an explicit code requirement. The decision to configure the primary OCPD below the standard 125% of the transformer's FLA should be approached with careful consideration, evaluating the specific characteristics of the transformer and the connected load. A prudent approach involves consulting with both the transformer manufacturer and the local electrical inspector. These consultations serve to verify the acceptability of the proposed configuration for the particular application at hand. This collaborative approach ensures that safety and code compliance are maintained while optimizing the overcurrent protection for the transformer. Let's delve deeper into the nuances of transformer overcurrent protection as outlined in the National Electrical Code, specifically focusing on Section 450.3. This section provides guidelines for the protection of transformers against overcurrent, which is essential for preventing damage to the transformer and ensuring the safety of the electrical system. Table 450.3 within this section is a critical reference point. It specifies the maximum overcurrent protection allowed for transformers based on their voltage and whether they have primary protection only or both primary and secondary protection. When only primary overcurrent protection is provided, the code mandates that the OCPD be sized no greater than 125% of the transformer's full load current. This is intended to provide adequate protection against sustained overloads. However, the code recognizes that in certain situations, particularly when both primary and secondary protection are present, a higher percentage is permissible. In such cases, the primary OCPD can be sized up to 250% of the transformer's full load current. This allowance takes into account the coordination between the primary and secondary protection devices. The rationale behind allowing a higher percentage for the primary OCPD when secondary protection is present is that the secondary protection device will respond to overloads on the secondary side, thereby protecting the transformer. This coordination allows for a higher setting on the primary side to avoid nuisance tripping due to temporary overcurrent conditions such as inrush current. Now let's address the scenario where the load on the secondary side of the transformer is small and fixed. In this situation, it may be tempting to reduce the size of the primary OCPD to save costs. While this may seem like a reasonable approach, it's crucial to consider the potential implications for transformer protection. The primary concern is whether the reduced OCPD size will provide adequate protection against overloads and faults. If the secondary load is indeed small and fixed, the transformer will likely operate well below its full capacity. In this case, a smaller primary OCPD may be sufficient to protect the transformer against overloads. However, it's essential to carefully evaluate the potential for future load growth. If there's a possibility that the secondary load will increase in the future, the primary OCPD should be sized accordingly to accommodate the increased load. Another factor to consider is the transformer's inrush current. When a transformer is energized, it draws a large inrush current that can be several times its full load current. This inrush current is a temporary phenomenon, but it can cause the primary op to trip if it's not sized appropriately. The magnitude of the inrush current depends on several factors, including the transformer's size, design, and the impedance of the source and load circuits. Smaller transformers generally have lower inrush currents compared to larger transformers. However, even small transformers can experience significant inrush currents that can cause nuisance tripping. To avoid nuisance tripping, it's generally recommended to size the primary op no less than 125% of the transformer's full load current, even if the secondary load is small and fixed. This provides a margin of safety to accommodate the inrush current and other temporary overcurrent conditions. However, in some cases, it may be possible to reduce the opt size below 125% if the transformer's inrush current is known to be low and the secondary load is carefully controlled. In such cases, it's essential to consult with the transformer manufacturer and a qualified electrical engineer to ensure that the reduced opt size will provide adequate protection. Now, let's discuss the specific question of whether it's a code violation to set the primary opt to 95% of the transformer's FLA to save costs. As mentioned earlier, NEC Table 450.3 specifies the maximum overcurrent protection allowed for transformers. It does not explicitly prohibit setting the opt below 125% of the FLA, but it does require that the opt provide adequate protection against overloads and faults. Therefore, whether it's a code violation to set the opt to 95% of the FLA depends on the specific circumstances. If the transformer's inrush current is low, the secondary load is carefully controlled, and a qualified electrical engineer has determined that the reduced opt size will provide adequate protection, then it may not be a code violation. However, if the transformer's inrush current is high, the secondary load is not carefully controlled, or a qualified electrical engineer has not determined that the reduced opt size will provide adequate protection, then it would likely be a code violation. It's important to remember that the NEC is a minimum safety standard. It provides guidelines for protecting electrical systems against hazards, but it does not necessarily provide the most optimal solution for every situation. In some cases, it may be necessary to exceed the minimum requirements of the NEC to ensure adequate protection. In the case of transformer overcurrent protection, it's generally recommended to err on the side of caution and size the primary opt no less than 125% of the transformer's full load current, even if the secondary load is small and fixed. This provides a margin of safety to accommodate inrush current, potential load growth, and other unforeseen circumstances. In addition to the NEC requirements, it's also important to consider the recommendations of the transformer manufacturer. The manufacturer typically provides specific guidance on the appropriate overcurrent protection for their transformers. Following the manufacturer's recommendations can help ensure that the transformer is adequately protected and that its warranty is not voided. In summary, determining the appropriate size for the primary opt of a transformer requires careful consideration of several factors, including the NEC requirements, the transformer's inrush current, the secondary load characteristics, and the manufacturer's recommendations. While it may be tempting to reduce the opt size to save costs, it's crucial to prioritize safety and ensure that the transformer is adequately protected against overloads and faults. Consulting with a qualified electrical engineer is highly recommended to ensure compliance with all applicable codes and standards and to determine the optimal overcurrent protection solution for the specific application. Now, let's discuss the inrush current of transformers in more detail. As mentioned earlier, inrush current is a temporary phenomenon that occurs when a transformer is energized. It's caused by the sudden change in voltage applied to the transformer's primary winding. When the transformer is first energized, the magnetic core is not yet magnetized. As a result, the transformer draws a large current to establish the magnetic field in the core. This inrush current can be several times the transformer's full load current. The magnitude of the inrush current depends on several factors, including the transformer's size, design, the impedance of the source and load circuits, and the point on the voltage waveform at which the transformer is energized. The worst case inrush current occurs when the transformer is energized at the zero crossing of the voltage waveform. At this point, the voltage is changing most rapidly, which results in the highest rate of change of magnetic flux in the core. This, in turn, induces the largest inrush current. The inrush current typically lasts for only a few cycles of the AC waveform. However, it can be long enough to cause the primary OCP to trip if it's not sized appropriately. To avoid nuisance tripping, it's important to consider the transformer's inrush current when selecting the primary OCP. There are several methods for mitigating the effects of inrush current. One method is to use a slow-blow fuse or a circuit breaker with a time delay trip characteristic. These devices are designed to withstand temporary overcurrents without tripping, allowing the inrush current to subside before the device operates. Another method is to use a pre-insertion resistor. This resistor is temporarily inserted in series with the transformer's primary winding when the transformer is energized. The resistor limits the inrush current, preventing it from reaching excessive levels. After a few cycles, the resistor is bypassed, allowing the transformer to operate at its full voltage. A third method is to use a solid-state soft starter. A soft starter is an electronic device that gradually increases the voltage applied to the transformer's primary winding. This allows the magnetic core to be magnetized gradually, reducing the inrush current. Soft starters are typically used for larger transformers where inrush current is a significant concern. Now let's discuss the importance of coordinating the primary and secondary overcurrent protection devices. As mentioned earlier, the NEC allows for a higher percentage for the primary OCP when secondary protection is present. This allowance is based on the coordination between the primary and secondary protection devices. The coordination of overcurrent protection devices is essential for ensuring that the electrical system is protected against overloads and faults in a selective manner. Selective coordination means that the overcurrent protection device closest to the fault or overload should trip first, while upstream devices remain unaffected. This minimizes the extent of the outage and allows the rest of the system to continue operating. To achieve selective coordination, the overcurrent protection devices must be carefully selected and coordinated based on their time current characteristics. The time current characteristic of an overcurrent protection device is a graph that shows the amount of time it takes for the device to trip at different levels of overcurrent. By comparing the time current characteristics of the primary and secondary overcurrent protection devices, it's possible to determine whether they will coordinate properly. In general, the secondary overcurrent protection device should have a faster time current characteristic than the primary overcurrent protection device. This ensures that the secondary device will trip first in the event of an overload or fault on the secondary side. The primary overcurrent protection device should be sized to protect the transformer against overloads and faults on the primary side, as well as to provide backup protection in case the secondary device fails to operate. Coordinating overcurrent protection devices can be a complex task, especially in large electrical systems. It's often necessary to use specialized software tools to analyze the time current characteristics of the devices and ensure that they will coordinate properly. Consulting with a qualified electrical engineer is highly recommended to ensure that the overcurrent protection devices are properly coordinated. Finally, let's discuss the importance of following the transformer manufacturer's recommendations. The transformer manufacturer typically provides specific guidance on the appropriate overcurrent protection for their transformers. This guidance is based on the transformer's design, operating characteristics, and potential fault currents. Following the manufacturer's recommendations can help ensure that the transformer is adequately protected and that its warranty is not voided. The manufacturer's recommendations may include specific information on the type of overcurrent protection device to use, the appropriate size of the device, and the coordination requirements for the primary and secondary protection devices. It's important to carefully review the manufacturer's recommendations and to follow them closely. In addition to the manufacturer's recommendations, it's also important to consider the specific application requirements. The operating environment, load characteristics, and potential fault currents can all affect the selection of overcurrent protection devices. Consulting with a qualified electrical engineer is highly recommended to ensure that the overcurrent protection devices are properly selected and coordinated for the specific application. In conclusion, transformer overcurrent protection is a critical aspect of electrical system design. It's essential to carefully consider the NEC requirements, the transformer's inrush current, the secondary load characteristics, the coordination of primary and secondary protection devices, and the manufacturer's recommendations. Consulting with a qualified electrical engineer is highly recommended to ensure that the overcurrent protection devices are properly selected and coordinated for the specific application.